This API returned 10 orders. The response looked perfect. But Postgres processed 1 million entries to find them. The database's own work report shows 1 million. Only 10 reached your app. Its sorted shortcut was working. The query had no error. The database did exactly what it was asked. It walked past 999,990 entries. Then it returned 10. The reason is one innocent number inside the query. Here is the request. Nothing looks dangerous. The API returns 10 orders per page. Page 1 skips nothing. Page 2 skips 10 orders. Page 100,000 skips 999,990. A common page number API turns that number into two instructions. Limit 10 means keep 10 results. Offset 999,990 means discard everything before them. That second instruction causes the discarded work. We usually imagine it differently. We imagine the database jumping directly to the requested position. It does not receive that instruction. It receives an ordered stream and a discard count. Offset is not an elevator. It is a counter. Watch how that counter grows. Page 1 produces 10 entries. Page 10 produces 100. Page 1000 produces 10,000. Page 100,000 produces 1 million. The response always contains 10. The discarded work keeps growing. Most people will never click next 100,000 times. Software can. Exports, crawlers, sync jobs, and integrations can walk an entire list. That is how a harmless page number becomes production work. Picture 1 million order cards on a conveyor. They are already in the correct order. The first card reaches the gate. The database counts it, then throws it away. The second card arrives. Count it, throw it away. The same thing happens again and again. The green tray still holds nothing. The red counter keeps climbing. 10,000, 100,000, 500,000, 999,000, 990. Only then does the gate change direction. The next 10 cards enter the green tray. Those 10 become your API response. The database did not misunderstand the request. It followed it exactly. To discard the first results, it first had to produce them. That is the false mental model to replace. A position in a result is not a saved drawer number. It is a count through one ordered result. Postgres can show us its work. The tool is called Explain Analyze. Think of it as the database's work report. We only need two numbers. At the bottom, the sorted shortcut produced 1 million entries. At the top, the limit returned 10 rows. That does not mean Postgres fetched 1 million full rows. In this test, it processed 1 million shortcut entries. That difference matters. So I ran a second check. This version selected only the ID stored in that shortcut. Postgres never fetched the full table rows. The plan reported 0 table visits. It still produced 1 million shortcut entries. The shortcut removed expensive work. It did not remove the discard count. On this machine, the deep page took about 133 milliseconds. The bookmark version took about 0.03 of a millisecond. Do not memorize that speed difference. Your hardware and data will change it. Remember the work instead. 1 million entries for one query, 10 entries for the other. The usual advice is to add a sorted shortcut. That sorted shortcut has a name. It is an index. This table already had one. Its primary key created it. Postgres used it. It supplied the IDs in order. In this plan, Postgres did not sort 1 million rows first. That is a major improvement. But the index answers one question. What entry comes next in this order? It cannot rewrite your request. Your request still says to discard 999,990 answers. A faster conveyor still counts every discarded card. Another query may choose a different plan. It may sort rows. It may scan a table. It may scan an index. So never say offset always scans the whole table. Say the accurate thing. Skipped results still have to be produced by the chosen plan. This pattern already sits inside familiar tools. Django warns that high page numbers can become slow. Its page helper eventually asks the database to use limit and offset. Odoo also exposes offset and limit in its APIs. Neither tool is broken. Using an offset is not automatically a problem. The risk appears when a growing table allows very deep requests. Speed is only the first problem. Positions can move between requests. Start with 6 orders, newest first. Page 1 returns 3. Your app now asks for page 2, but before that request arrives, someone creates order 110. It enters at the top. Page 2 still says to skip 3. The first 3 are now 110, 100, and 90. The next row is 80. You already showed 80 on page 1. The user sees it twice. Off did exactly what it promised. It did not remember the earlier page. It counted again from the current top. A later request can see rows saved after the earlier request. The numbered positions moved underneath it. Now change the question. Do not ask for page 2. Remember the last order the user saw. That order was 80. Ask for the next 3 orders below 80. Postgres can use the index to seek near 80. Then it reads the next entries. The new order 110 does not move this bookmark. The request is no longer based on a position. It is based on a value. This is called keyset pagination. APIs often send the value inside a cursor. Here, a cursor simply means a bookmark. It does not mean an open database cursor. On the million row test, the bookmark query returned the same 10 rows. Its index scan produced 10 entries. The deep offset query produced 1 million. With the matching index, this work can stay roughly flat on deep pages. There is one easy way to build this badly. Imagine an activity feed sorted by creation time. Your cursor remembers the last timestamp. The next request asks for rows older than that time. That sounds correct, but timestamps can repeat. 5 orders may share the same timestamp. Page 1 returns IDs 5, 4, and 3. The cursor remembers only their time. The next query asks for anything older. IDs 2 and 1 have the same time. They're not older. They vanish between the pages. The bookmark needs the complete order. Sort by time first. Then sort by ID. Now the bookmark remembers both values. The time finds the group. The ID breaks the tie. Postgres can compare the pair directly. The next page returns IDs 2 and 1 before moving to older times. Every row now has one exact place. That is what makes the bookmark safe. The bookmark is not a free upgrade. It changes what your API can promise. An offset API can request page 100,000 immediately. A bookmark cannot. You need an earlier bookmark before you can continue. That makes numbered page buttons harder. That trade-off should follow the interface. A search screen may genuinely need page numbers. An activity feed may need only a continue button. Those are different product promises. Moving backwards needs a reversed query and careful ordering. The bookmark also belongs to one filter and one sort order. Change either one and the old bookmark may mean something else. The order and values should stay stable. If they change, rows can move around the bookmark. The matching index still matters. Without it, Postgres may scan or sort far more data. And the bookmark does not freeze the feed. New rows can still appear. Existing rows can still change or disappear. Its promise is smaller. It anchors your progress to one exact row. It avoids recounting from the top. It also avoids the position shift from a new row above your bookmark. Use offset for small lists and shallow pages. Keep it for admin screens that truly need numbered page jumps. Use a bookmark for large feeds, infinite scroll, exports, and sync jobs. Choose the contract your interface actually needs. Do not remove every offset tomorrow. Open the deepest page your users can reach. Test that exact query on staging or a safe copy. Read the actual row count in Explain Analyze. Look at the step feeding the limit. If 10 rows come out after enormous work, you found the discarded work. Then ask one product question. Must the user jump to any page number? If yes, offset may be the honest cost. Does the user only continue from the last item? If yes, a bookmark is usually the better contract. Give that bookmark every value in the order. Add a unique value to break ties. Build the matching index. Then test the deepest real request again. One sentence is worth remembering. Offset says, count past the earlier results. A cursor says, continue after this exact row. The API returned 10 rows. Now you know where the other 999,990 went.